Hello! So today we're going to be talking about null space and column space. When I say the word null, what's the first thing that pops into your mind? Something to do with zero, right? So that's how we're going to be defining our null space. Something to do with zero. Or more formally, we're going to be defining our null space, denoting it NS of A. So kind of like no sugar added, but I promise there's plenty of sugar in the null space. It's going to be equal to the set of all x vectors in our vector space such that this equation, our a times the x vector, is equal to 0. So basically we're looking at all the times that we can take a matrix and multiply it by something that's not the 0 vector and it still give us the 0 vector. Whoa, that's wild, right? We're used to having, when we multiply two things together, and we get 0 out, one of them has to be 0. It's what we're used to. But in this case, our null space is a very special place where we have some vectors x that when we multiply them by our matrix A, we're going to get the 0 vector out. So let's find the null space of this matrix here of A. So our first step in finding the null space is to reduce our matrix A down to reduce our echelon form as we augment it with the 0 matrix. We have our A and we're going to augment that with the 0 vector. Now we're going to go ahead and row reduce this. We're going to first get our pivot variable in our first column by itself. So we're going to take 3 row 1 plus row 2 is going to be our new row 2. And we're going to simultaneously take negative row 1 plus row 2, or row 3 is our new row 3. So this is going to give us the same as the first one. And then 3 times 1 plus negative 3 is 0. 3 times 2 is 6 plus negative 6 is 0. 3 times negative 1 is negative 3 plus 4 is 1. And then 3 times negative 2 plus 9 is 3. And then 0 times 3 plus 0 is just 0. And then we're going to do our next row operation, and we're going to take negative row 1 plus row 3. So we have negative 1 plus 1 is 0. Negative 2 plus 2 is 0. Negative 1 times negative 1 plus 1 is going to be 2. Negative 2 times negative 1 is going to be 2 plus 4 is 6. And then negative 1 times 0 plus 0 is 0. Okay, so now we have our next pivot variable right here, and we're going to want to get that to be the only non-zero term in its column. So we can do that by taking row 2 plus row 1 is our new row 1, and negative 2 times row 2 plus row 3 is our new row 3. So with that, we're going to get this matrix. We're not doing anything to row 2, so let's just copy that on in here. And then we're going to have our row 2 plus row 1. So 1 plus 0 is 1, 2 plus 0 is 2, negative 1 plus 1 is 0, and then negative 2 plus 3 is 1. And then 0 plus 0 is 0. And then we're going to have negative 2 times row 2 plus row 3. So negative 2 times 0 plus 0 is 0. Negative 2 times 0 plus 0 is 0. Negative 2 times 1 plus 2 is 0. And then negative 2 times 0. Negative 2 times 3 plus 6 is 0. And then negative 2 times 0 plus 0 is 0. So this is our matrix in reduced row echelon form. So remember that this is trying to solve our equation here. So basically we are trying to solve, so when we are solving this, we're going to get a system of linear equations. So we're going to have x1 plus 2x2 plus 0x3 plus x4 is equal to 0. And we're going to have 0 times x1 plus 0 times x2 plus x3 plus 3x4 is equal to 0. So from this, we have our x2 and x4 as our free variables. You see there's no pivot variable in these two columns corresponding to x2 and x4. So then we can write this as x1 is equal to negative 2x2 minus x4. and x3 is equal to negative 3x4. Okay? We want to find all of the vectors that satisfy this equation. So that's going to be all of these vectors of x1, x2, x3, x4, such that these are true. So we know that x1 is going to be negative 2x2 minus x4. x2 is a free variable, so it's just itself. x3 is equal to negative 3x4, and then x4 is just equal to x4. So we can write this as a linear combination of two vectors in R4, and their coefficients are going to be our free variables. So we're going to first pull out our x2. There are negative 2 x2's in our first entry, 1 in our second entry, 0 in our third entry, and 0 in our fourth entry. And then we're going to add it to x4 times we're going to have negative 1 x4 in our first entry, 0 in our second entry, negative 3 in our third entry, and 1 in our last entry. So what this is telling us is any linear combination of these two vectors is going to be a solution of our null space. So we can write our null space as this. So our null space of our matrix A is going to be equal to, okay, so it's any linear combination of these two, right? So remember, we have a fancy word for that, and it's going to be equal to the span of these two vectors in R4. So our null space is any linear combination of these two vectors. And what does that linear combination do? If we take any linear combination of these two vectors and plug it into this equation, so if we take our matrix A times any linear combination of these two vectors, we're going to get the zero vector out. Don't believe me? Let's try it. Let's go right here. And if we take a linear combination of these two vectors here, let's just try adding them together. So have x2 and x4 both be equal to 1. So we'll just have, right up here, we're going to take negative 2, 1, 0, 0 plus negative 1, 0, negative 3, 1. And that's going to be equal to negative 2 plus negative 1 is negative 3, 1 plus 0 is 1, 0 plus negative 3 is negative 3, and 0 plus 1 is 1. So now if we take our matrix A and multiply it by this matrix here, we're going to take A, and if we multiply it by this linear combination here, negative 3, 1, negative 3, 1, what's that going to give us? We're going to have negative 3 plus 2, so it's negative 1, plus 3 is going to be a 2, minus 2 is going to give us a 0, and then we're going to have 9, so negative 3 times negative 3, plus negative 6, minus 12, so that's going to give us a negative 9, plus 9 is going to give us a 0, and we're going to have negative 3 plus 2 minus 3 plus 4 is also going to give us a 0. So look, this linear combination is going to give us the 0 vector back out. Whoa, wild! So our null space is defined as all of the linear combinations of these two vectors that are going to give us a 0 vector out. So when we analyze here our null space, we see that basis of it has dimension 2. So our basis here is these two vectors. Because they're literally independent, since we only have 2, we just have to check to make sure they're not multiples of each other, which they're not, so we're in business. And the dimension is 2. You'll notice that that corresponds to the two columns here that do not have a pivot variable, or we also see here that means that we have 2 free variables, and that corresponds to our 2 dimensions here for our basis of our null space. So now we have a really good friend that we want you all to meet, and it's called the column space of A, and that is going to be a good friend of our null space. So let's take some time to get to know the column space.